Hello everyone, welcome back to Mr. Exams Professor. We successfully completed the basics of algorithm analysis, time complexity, space complexity, and asymptotic notations. Now we are moving to one of the most important topics in Unit 1, AVL Trees. In today's class, we are going to start AVL Trees completely from the basics. If you've never studied AVL Trees before, don't worry. I'm going to explain everything step by step. Before understanding AVL Trees, we first need to understand a very important data structure called a binary search tree or a BST. Then we'll understand the problem that occurs in the normal BST, and then we will see how the AVL trees solve the problem. Finally, we will understand the most important concept in AVL trees, the balance factor, and we will also understand why an AVL tree allows only -1, 0, and +1 as balance factor values. So let's start from the very basics, and this is very important for you. So in this session now, I'm going to explain the following contents that I have written in the notebook. So we're now going to dive into the introduction, the binary search tree revision, problem with BST, AVL tree, height balance tree, and balance factor. So the most important one, why -1, 0, and +1. So yeah, just come on. So before understanding AVL trees, let's quickly revise binary search tree. That is nothing but a BST. So a binary search tree is a special type of binary tree in which every node follows a specific order properly. So like, for every node, left subtree is less than root, less than right subtree. So this is the most important property of a binary search tree. For any particular node, all the values in its left subtree are smaller than the node. All the values in its right subtree are greater than the node. So I'm now drawing the picture of it. So let's say, for example, any number like 50, 30, greater than 30, and say 70. Here is the 20, here 40, 60, and 80. So let's take an example. Here 50 is the root node. 50 here is the root node. On the left side we have 30. Since 30 is smaller than 50, it is placed on the left. On the right side we have 70. Since 70 is greater than 50, it is placed on the right. Now look at 30. Its left child is 20 because 20 is smaller than 30. So its right child is 40 because 40 is greater than 30. So the binary tree property is maintained. So now let's do the search operation. Search operation. Suppose we want to search for the value 60. Point out to the tree. First we compare 60 with 50. Therefore we move to the right. Now we compare 60 with 70. 60 is smaller than 70. Therefore we move to the left. We find 60. So we don't have to check every node. That is why a well-balanced BST can perform searching efficiently. So now the problem with an ordinary BST. So students, there is a problem. A binary search tree is not always balanced. So this is important. A binary search tree is not always balanced. Balanced BST. Skewed BST. Suppose we insert these values. For example, let's say 10, 20, 30, 40, 50. Let's insert these values one by one into a BST. So So it's a problem now, so let's solve it. So step 1, given 10. So this is very important for your examinations. Here I am writing like step as S, so please don't write like S2 in examinations. You have to write as steps so that you can get very good marks in the examination. So here 10, 20. So step 3, 10, 20, 30. So if you want additional add-ons, you can if you want to say any add-on in the examination, semester examination. So here step 1, we have written 10. So just write that. So we have take 10. So like that. It is important for an examination. So as it is explanation lecture, just I'm writing like this ideally. So now step 4. Here 10, 20, 30, 40. So step 5. Ten, 20, 30, 40, 50. So look at this tree carefully. Is this tree looking like a property? Like proper tree? It's almost looking like a straight line. As you observe. This is called skewed binary search tree. What is this called? Skewed binary search tree. Or skewed BST. So skewed BST ten, 20, 30, 40, 50. Height increases. Height increases, but performance decreases. This is the problem. So now I'm going to explain about why a skewed BST a problem. Why is skewed BST a problem? So now let's search for 50. Example. We start at 10, we start at 20. So I'm writing here. Now let's search for 50. We'll start at 10, 20, 30, 40 and 50. So how many nodes did we check? We used to check 5 nodes in total. So if we have 1 lakh nodes, for example, assume if we have 1 lakh nodes, arrange it like this. So we may have to travel through almost all the nodes. So the tree loses the advantage of being a tree. So what I am saying is a balanced BST has fast operations. Skewed BST, slow operations. So here, in a balanced tree, the height remains relatively small. In skewed tree, the height becomes very large. Therefore, we need a tree that automatically maintains balance. There is where AVL tree comes into the picture. So now one of the important topic I'm explaining now. So what is an AVL tree? AVL, Adelson-Velsky and Landis. Velsky, yeah, Velsky. What is Landis? Yeah, Landis. AVL stands for Adelson, Velsky, and Landis. It is named after two computer scientists who introduced this tree. An AVL tree is a self-balancing binary search tree. This is important. An AVL tree is self-balancing binary search tree. This is important. This is where you get more marks in the examination. So if you write these type of points there, so by this we can say that AVL tree is a self-balancing tree. So what is a binary search tree? It follows left subtree is then root is then right subtree. So what does self-balancing mean? It means that after operations such as insertion and deletion, the tree checks its balance and performs adjustment whenever necessary. These adjustments are performed using rotations. So AVL tree is equals to BST plus self-balancing. So what is a height balancer tree? Height balancer tree. So height balancer tree means a height balancer tree. Just kidding. Okay. Now we need to understand one more important term. Height balancer tree. A tree is height balanced when the heights of the left and right subtrees of a node do not differ by more than one. This is important. When the heights of the left and right subtrees of a node do not differ by more than one. This is a height balancer tree. So height balancer tree difference in heights is less than or equals to 1. This is also important. Height balancer tree in heights less than or equals to 1. Do note this. So in simple words, the left side and right side should not have a largely difference in height. The tree should not become heavily titled to one side. So now balance factor. Balance factor. Balance factor. So balance factor is a numerical value used to determine whenever a node is an AVL tree is balanced or not. To calculate the balance factor of a node, we take the height of its left subtree and subtract the height of the right subtree. So like balance factor equals to height of left subtree minus height of right subtree. So this is what I told earlier. But in some more professional words, like what I told is, the balance factor is a numerical value used to determine whether a node is an AVL tree is balanced or not. And to calculate the balance factor of a node, we take the height of its left subtree and subtract the height of its right subtree. So you can write in your own words, but it should have a meaningful sentence so that the examiner can use it to understand what you have written in the examination. So I'm going to give an example for the balance factor. So let's take, earlier we have took the values like 50, 20 and 30, so on, like 50, 30, 60. No, I'm now going to write 70 here. So for node 50, the left subtree has height 1. So the right subtree has height 1. Therefore, left height equals to 1. Right height equals to 1. So 1 minus 1 equals to 0. Therefore, balance factor of 50. So balance factor of 50 is 0. So I can write like balance factor of 50 is equals to 0. So therefore, node 50 is balanced. I hope you understand this. So balance factor now plus 1. I'm writing balance factor as BF. It's not something what you think, it's balance factor BF. That's it. So here, for a better understanding, let's take the same values what you have taken earlier. So 30. So now the left subtree has greater height. So left height is equals to 1. Left height is equals to 1. Right height is equals to 0. Therefore, 1 minus 0 is equals to plus 1. So balance factor is equals to 1 minus 0 is equals to plus 1. So balance factor minus 1. So here 50, 70. So the right subtree has greater height. Left height equals to 0. Left height is equals to 0. Right height is equals to 1. So 0 minus 1 is equals to minus 1, obviously. So I can say that balance factor of 50 is equals to O minus 1 equals to minus 0 minus 1 equals to minus 1. So the balance factor is minus 1. This is also allowed in an AVL tree. So now one of the most important topic here. Why only minus 1, 0 and plus 1? This is the question you specifically wanted to explain properly. Like if the examiner asks the questions in the examinations like why you use only minus 1, 0 and plus 1, like why not minus 2 and so on other numbers. So AVL allowed balance factors minus 1, 0, plus 1. Students, now comes the most important question. Why does an AVL tree allow only these numbers? Like minus 1, 0 and plus 1. Why not like as I've told like plus 2, plus 3, minus 4, so on, etc, etc. Now let's understand. So I'm going to explain this with an examples. Case 1, BF equals to O, 0, 0, 0, balance factor. So both sides have equal height, so the difference is 0. The tree is perfectly balanced. Perfectly balanced. So BF equals to 0, perfectly balanced. So case 2. I'm writing case as C, but you have to write in the examinations as case so that you can get good marks. So here BF equals to plus 1. So 50, 30. So the left side is only one level taller. This is still considered balanced. So BF equals to plus 1, left heavy, yet but balanced. So now comes BF equals to minus 1. In case 3, BF equals to minus 1. Right side here right side is only one level taller. This is also considered balanced. BF equals to minus 1, right heavy but balanced. So for example, if I for better understanding, why not the number I've told plus 2? So now I'm going to say plus 2. So let's draw this like 50, 30, 20. So let's calculate this. So let's calculate here. So left height is equals to 2, right height is equals to 0. So BF equals to 2 minus 0, BF is equals to plus 2. So here the left side is 2 levels taller than the right side. The tree is now significantly unbalanced. Therefore plus 2 is not allowed in an AVL tree. When the balance factor becomes plus 2 or minus 2, the AVL tree considered unbalanced and we need to perform a rotation. So BF equals to plus 2, unbalanced. So rotation required. Basically rotation required. So then what happens is, so BF equals to minus 2, unbalanced, rotation required. So the most important one I'm going to say, so remember students, minus 1, 0, plus 1 are only allowed balance factor values in an AVL tree. These are the only allowed ones, because these values indicate the difference between the heights of the left and right subtrees is at most 1. If the difference becomes 2 or more, the tree becomes unbalanced and may lose its efficiency we expect from a balanced search tree. Therefore, when the balance factor becomes plus 2 or minus 2, the tree needs rebalancing. This rebalancing is done using rotations. So the rebalancing is done using rotations. Note this. So now I'm going to say about the rotations. So like first, okay, unbalanced AVL tree. Unbalanced AVL tree. BF equals to plus 2 or minus 2. Rebalancing, and therefore rotation. So students, don't worry if the word rotation is new to you. So in the next video we'll study rotations from the absolute basics. We will study them one by one, like LL rotation, RR rotation, LR rotation, RL rotation. We will not learn all 4 at once. We will take one rotation at a time, draw the tree, insert the node, identify the imbalance, and then perform the rotation step by step. So this is the end of the theoretical part I'm going to say. So like if I'm going to say for an exam oriented definition, an AVL tree is a self-balancing binary search tree in which the difference between the heights of the left and right subtrees of every node is at most 1. I have explained that. So balance factor BF equals to height of the left subtree minus height of the right subtree. Allowed values in AVL is -1, 0 and +1. So these are the important definitions for your semester examinations. If the questions ask define AVL tree or what is an AVL tree, you can write this definition. So hope you enjoyed this session, hope you understood this. So I'm now giving important questions which is useful for you. So first question, define an AVL tree. What is self-balancing BST? What is self-balancing BST? What is a balance factor? What is a balance factor? Okay, also a formula. Okay, this is another question. So let's include this as another question. What is the formula for balance factor? So fifth one is what are the allowed values in balance factor in an AVL tree? Okay, allowed balance factor values in AVL tree. Why only -1, 0 and +1 are used? So what is a skewed BST? What happens when BF equals to +2 or -2? And why is balancing required? Why is balancing required in BST? So what is the full form of AVL? AVL's full form. What is AVL? So these are the important questions. So please read the concept that I have explained and do see these questions. These are very important basic level and also important questions. This is very important. So these are the conceptual oriented questions which I have given now after the explanation. Yeah, so students, in today's class we started AVL trees from the absolute basics. We first revised BST, then we understood the problem with the skewed BST. After that we learned what an AVL tree is and why it's called self-balancing binary tree. We also learned the most important concept, balance factor. So do remember that balance factor is equals to height of left subtree minus height of right subtree. The allowed values are -1, 0 and +1. If the balance factor becomes -2 or +2, the tree becomes unbalanced and rebalancing is required. So in next class we are going to learn the most important part of AVL trees, the rotations. We'll start with allele rotations. We'll draw the tree, we insert the node, we'll identify exactly where the imbalance occurs, and then we'll perform the rotation step by step. After that, we'll move to RR, LR and RL rotations. So make sure you watch the next lecture carefully because this is the foundation of the understanding AVL tree insertion and deletion. So if this video helped you, like the video, share it with your friends and subscribe to Mr. Exams Professor for complete semester oriented preparation. Thank you and I'll see you in the next class. Bye guys.